Right, here's the second part of this introduction to differentiation, and here we want to focus a little more specifically on what we call a derivative, which will be the focus of a lot, roughly half, if not more, of the work we do in calculus. So let's look at this nice simple graph here. I got the graph of f of x, which if you look at it, you see it's x squared, so I'll just kind of say here, f of x is x squared. And you can see this point at 2, or if I look at the coordinates of this point, it's at 2, 4. And I want to first start by visualizing what the tangent line of this function is at this point. Now, a tangent line is a line that, if I zoom in, it's a line that it's not the most scientific or proper language, but just barely touches the function, and it matches the slope as much as possible at this point. So for example, if I'm going to draw a tangent line here, this is a terrible tangent line right there. That's a terrible tangent line. And so a tangent line for this should, as much as possible at this point, match the slope of it there. So something like that. Try that a little once more. Again, I am sort of estimating here, so. That took a while, but there we go. Okay, there's my estimate of this tangent line. And so we say that's the line tangent to f of x at this point, 2, 4. Or this is the line tangent to f of x when x equals 2. Well, the slope of that line represents the derivative of this function at that point. And if you look right here, I want to estimate that f with an apostrophe. We pronounce that the derivative of f, or we can say f prime, but that apostrophe there represents not the function at 2, but the slope of the function when x equals 2. The derivative of the function, or the gradient of the function when x equals 2. And so since I've already sketched this tangent line here, if I want to estimate what the derivative of this function when x equals 2 is, I need to look at this line and estimate the gradient or the slope of this line. And I define the slope of any function, any line, and see 2 points. So I know it goes through 2, 4. It seems to go through something close to this point up here, which is, 3, 8. But I don't really care about the coordinates. I can see the slope or the gradient. I go up 4 over 1. So this line approximately has a slope of 4. And so my estimate for f prime at 2, or my estimate of the derivative of this function at 2 is 4. It's an estimate because I'm all basing this on this sketch of a tangent line that I just drew with a ruler. And it's got to be a decent estimate, but it is just an estimate we want to keep in mind. And there's nothing special about the number 2. It's just an easy point to look at. At different points in this function, it would have a different slope. It would have a different derivative. All right, so that's my estimate. I now want to actually calculate it exactly, first by using the slope formula to find an exact value. Now, this can get deceivingly tricky quickly, so we're actually not going to do this a lot in this course, although I'll show you one way here. And so the slope formula, the change in y over the change in x. That's a weird-looking delta. Let's try that again. Change in y over change in x. So we generally use this y2 minus y1 divided by x2 minus x1. So in this case, I already have a point here, 2, 4. But to find the slope, I need another point. But keep in mind, I don't need this tangent line anymore. I want to look at another point on the actual function. So maybe I'll just imagine a point right here. But I don't actually care about the coordinates of that point I just drew, because the idea is I want to imagine finding the slope where these points get closer and closer to each other. The closer these points get to each other, the more that the slope between them gets closer to the exact derivative when x equals 2. And like I said, what I'm going to do is deceivingly difficult, even though we'll see other ways around it later on. So that point there in red, where is it? Well, the x coordinate is just x, because I want to imagine that point being dynamic. I want to imagine it being movable. It's not a fixed point like that 2, 4. The y value, I could say y, but don't forget y is the same as x squared. And so I'm going to call this x squared. And so I'm going to imagine this being my y1 sorry, let's get my variables right. I'm going to think of this being my x1 and my, actually, let's make this, it doesn't really matter. Let's make this x1, y1. Let's make this x2, y2. And so using my slope formula, y2 minus y1 will be x squared minus 4 over x minus 2. So x squared minus 4 over x minus 2. But again, if I'm trying to find the derivative or the gradient of this function x equals 2, I want to imagine these this point here getting infinitely close to this point here. And so that the line between them, we call that a secant line, gets closer and closer to the exact tangent line. And so I want to imagine that this change in x approaches 0. So what we're really doing is we're finding the limit as the change in x approaches 0. However, that means if I just try to directly work this out, that means I'm trying to make x minus 2 0. But then I'm dividing by 0, so I can't do that. So what can I do? Well, I can notice, conveniently enough, that my numerator can be factored. It's a difference of squares. So x squared minus 4 is the same as x minus 2 times x plus 2. Divided by x minus 2. And I can then simplify this expression because my factor of x minus 2 cancels out, which means this derivative behaves the same as just the simple expression x plus 2. And now there's nothing stopping me from just substituting this value of 2 into here. So I can now see, okay, by doing a bit of factoring and simplification, that the derivative when x equals 2, or f prime at 2, must be the exact same as 2 plus 2, instead of x, I have 2. So it really is exactly 4. So my estimate up above, I now know is perfectly correct. Keep in mind, if I want to find the slope at a different point, I could do the exact same thing. Let's say I want to find the slope at this point right here at 1, 1. I would just I'd have to change this part here to be x squared minus 1 over x minus 1, which in that case, I could factor it as well. I get something similar. But just keep in mind, it's not like we can always factor expressions quite as pleasantly as before. So I am keeping things relatively simple by being careful about what sort of expressions and points we're choosing. However, even just this took a bit of time just to get this 4. And to be honest, your GDC can at least estimate it extremely quickly. So this is where now you need to be familiar with your own GDC. In general, though, on most, you want to first graph the function. So like on a TI-84, you want to first graph this function, x squared. Make sure you can see enough for, for example, if I want to find the derivative of 2, make sure you can see the point where x equals 2. And then you should be able to quickly just find the value at that point. And so this is where you just need to become familiar with your own, and you should get 4 or extremely close to 4. Keep in mind, it is an approximation. I think on the TI-84, you get 4.000001 or something like that. But it's really, really quick. And so that's really now the focus of this second part, which is now using our GDC to evaluate all of these. And so, as always, your job is to be familiar with your own GDC. With a little bit of practice, it's really, really quick. So for g prime at 3, you would probably want to first graph 2 to the power of x, making sure your window settings are setting it up so you can actually see when x is 3. And so you should then get, for g prime at 3, you should get approximately to 3 significant figures, 5.55. I'll just switch to Desmos here for a second. Because when you look at this graph, again, when x equals 3, that's this point right here, 3, 8. And as long as you can see that point on your screen, you should quickly be able to find the at least approximate derivative at that point. All right, so for the next one, using different notation, I want to find dy dx, which means the derivative when x equals 4 of this function. And there's lots of different ways to denote derivatives. And that said, this and this are probably the 2 most common. If we're using function notation, we tend to just put an apostrophe in front of it. If we're not using function notation, if we're saying y equals an equation, we can say dy over dx, which is, you can see, is related to the slope formula. Either way, in this time, ideally you know how to use your calculator, and so dy dx should be approximately negative 0.0556 to 3 significant figures. And if I just switch to my graph here for a second, Here is the function we just looked at. Here is the point. And notice if I zoom in on this point here, notice if I zoom in enough, it looks like a linear function at this point, and the slope of this is just barely going down, so it makes sense it's a negative number, but relatively close to 0. And next, what is h prime of x? H prime of 0, the derivative at 0 for x cubed minus 2x squared. And if you do that, you should get a derivative of exactly 0, or really, really close to 0, depending on how well it's approximating it. And if I look at the graph for this, I can actually see this quite nicely from the graph. Here is the graph of x cubed minus 2x squared. And so when x equals 0, that's this vertex. And notice when I zoom in enough, it looks like a perfectly horizontal line. Remember, the slope or the gradient of a horizontal line is 0. And in general, a derivative of 0 ends up being a really important point. It ends up usually being a maximum or a minimum or something like that. But we'll see those lots. But derivatives equaling exactly 0 quite often lead to these vertices here. Not always, but quite often. All right, so the last one like this, I want the equation of the tangent line to y equals 8 over x when x equals 2. So this relies on being familiar with your GDC, which again is your responsibility to figure out. It's fairly quick. First, what I'll do though is just find the derivative, and so dy dx, we should get approximately negative 2 when x equals 2. That said, to find the actual equation of it, it should be pretty quick. For example, in the TI-84, once you found your derivative, you go to the draw menu and you pick tangent, and it just draws it, and you get a tangent equation that, which keep in mind, may not be exact what it's telling you, but it comes to pretty much y equals negative 2x plus 8 is our tangent, equation of the tangent. I'll just kind of show this in Desmos really quickly here. So here is the function and the point. There we are. There's that point right there. And so the tangent line I just found, I just graph here, and that's, you can see, is a dashed line in red. And notice as I zoom in, you can see the closer I get, the more and more that tangent line matches the gradient, the slope of the function. At this point, they seem identical. You know they're not, just from the naked eye, they seem identical. Really important to be familiar with your GDC for this, because that is an expectation of the course. Remember, you're always allowed to use it. And so with a little bit of practice, it should be quite quick. Lastly, other way around, I have a blank grid here. I have 6 characteristics of a function, and we want to graph something that matches all of this. And so I will, while there's infinitely many correct answers, I'll try to come up with something that's relatively simple. And so the first 3 have nothing to do with derivatives. They're just describing a point. So if I look at the first one, f at negative 5 equals 3, that means when x equals negative 5, y equals 3. So that means I know it goes through negative 5, comma 3. I know it goes to that point right there. f0 equals 0 means when x equals 0, y equals 0, which means it goes to the origin. And here, f4 equals negative 3 means when x equals 4, y equals negative 3. So here. So I know the graph goes to these points. Okay, that's it. The next 3 are looking at the derivative. So f prime at negative 4, which means the derivative of f at negative 4 is 0, which means when x equals negative 4, this graph has a slope that is 0, or the tangent, the slope of the tangent line at this point is 0, which we saw from a previous example right here. Can be visualized quite simply as a vertex either like this or like this. And so at this point, you know, I can imagine something like this or like this. I'll just leave those for a moment. Next, I have when x equals 0, the derivative is negative 1, which means right here, right at the origin, the slope at that point is exactly negative 1, which is a pretty easy thing to visualize. Negative 1 looks something like this, so I'll keep something like this. Okay, being willing to adjust, but that's what a slope of negative 1 looks like. And then lastly, f prime at 4 equals 0 means when x equals 4, the slope, the gradient, is again at 0. So I can imagine something like this or like this. So put it all together, I can see what'll work quite nicely is perhaps something like this, where it kind of comes from here, goes down, and then goes back up. And there's other possibilities, but that is relatively simple and will work. So I'll just erase all my mess and just kind of draw this more pleasant nicely now. So something like this has a vertex right there. So right when x equals -5, it has a slope of 0. And then right at when x equals 0 has a slope of -1. And as it gets close to this other point, it kind of flattens out. And then it doesn't actually have to go back up. It could go back down. But just to keep things kind of familiar, make this look almost like a wave, I'll just go like this. All right, lots of examples that will work, but this is, I think, probably the simplest one that fulfills all the constraints.